My colleague once told me that if you have a snazzy title to a presentation, it'll make people want to listen to it more. So here's my feeble attempt at that. So Livermore Computing, that's the kind of the division that runs the HPC resources at Lawrence Livermore National Lab. That's where I'm at. A little bit about the lab. If you don't know, Livermore Lab is in Livermore. If you don't know where Livermore is, it's about an hour, hour and a half, kind of east, northeast from here, depending on traffic. And right now, it's a beautiful time to visit. We have green hills about 3 months out of the year, and that's right now after the rains. So you can take a detour and drive through there. A little bit of history for the lab. It was farmer fields until World War II, and Navy commandeered some fields and turned it into a naval air station. And then some weapons designers at Los Alamos got into an argument with Oppenheimer and others. They wanted to go a different route and with design, and so they were given leeway to come up, and they set up shop here in Livermore. At this time, it was an offshoot of the University of California's Berkeley radiation lab. So they kind of took over there, did design work, officially was renamed to Lawrence Livermore National Lab in 1971. There's still a bit of a competitive nature with Los Alamos. That's for kind of professional scrutiny and making sure that we go through rigorous design reviews and such like that. There's a lot of collaboration too. Currently, there's about 9,000 employees, which is 50% more than there were 10 years ago when I joined the lab. So it's grown quite a bit. So what do we do? As I mentioned, there's a lot to do with nuclear design, nuclear weapons design. So there are 3 labs, Sandia, Los Alamos, Lawrence Livermore, that are kind of termed the tri-labs. We're under the National Nuclear Security Administration, or NNSA, which is an agency inside of the Department of Energy. And that's our primary mission, is maintaining the nation's nuclear stockpile, but also currently modernizing that stockpile. Aside from that, we do a ton of other science, pretty much everything you can think of, from 3D printing to biology, to threats and stuff that's not threats. So really a science lab. So to do that science, there's a lot of computing, right? And both hardware and software. I think we have a pretty decent legacy of software, including Lustre. Back when, in the early 90s, when we realized we're going to have to go to computing to test nuclear weapons, there a number of programs came out of that. One of those was, I think, the ASCII program, and for, I think, Accelerated Strategic Computing Initiative, if I remember right. And so one of those initiatives was this Path Forward effort, and that funded the development of Lustre with, I think, Peter Braun, Carnegie Mellon University, then that moved to Cluster File Systems. If you want authoritative detail, ask Andreas. But beyond that, Slurm and Flux came out of the lab. Brian, my colleague down here, he led the development of ZFS on Lustre, which was then rolled into the overall Open ZFS project. We're a heavy ZFS shop. We think it's awesome. Brian's a superhero. And there's lots of other tools that you've probably used that have come out of the lab. So pretty good legacy. Of course, we also have hardware. You might have heard of El Capitan. We have, out of the last top 500 list in November, we have 13 systems that are on that list, including 2 in the top 10. And we figure we've got about 3 exaflops worth of compute power there right now. So we have a fair bit. And I took these slides from when I spoke at the Lustre BOF last November, because I really like the scale that it kind of shows, the scale of El Capitan. So if you look here in the red column, that's Sierra. Sierra was from our Coral 1 contract. Coral stands for collaboration between Oak Ridge, Argonne, and Livermore. And so out of that, Oak Ridge got Summit, and we got Sierra, and Argonne was supposed to get Aurora, and I'm actually not sure if Argonne got anything out of that contract. Someone will have to educate me later. But so Sierra came in at number 2 on the top 500 behind its sibling Summit, and it's been a workhorse. It's still going. It's still running, these top production jobs right now. And if you look at that chart, it pretty much, it's heads and shoulders above all of our other resources. It really dominates. But then last summer, we got Tuolumne, which is a much smaller sibling of El Capitan, meant for the unclassified network. And that more than doubled the performance of Sierra. Now, what's interesting is, if I have my facts right, Sierra, just the compute and infrastructure side of Sierra, is about 240 racks. Tuolumne is 10 compute racks. They're bigger racks, mind you. These Cray systems are big, but 10 racks of compute more than double the performance of 240 racks of Sierra. So that was pretty mind-boggling. Of course, then you add El Capitan, and Tuolumne, the second column there, is just a peon. It's almost nothing, right? And Sierra, still in red, is even less, right? And our other compute resources that are on the top 500 don't even peak their head above the line there. So I think this is a good job of showing just how massive El Capitan is. It's pretty big. So El Capitan is a rock, right? I'm curious, maybe raise your hands. How many of you have been to Yosemite National Park? Okay, that's a pretty good showing. For those of you that don't raise your hands, you need to repent and go. Yosemite is stunning. It's beautiful. So make that a priority on your bucket list of things to do. So if you look at the mural on the front of the rack here, El Capitan is, well, it's kind of hard to see, but if you look on the the left side, there's a kind of a whitish cliff sticking out of the picture, and that's El Capitan, this big sheer rock. So we have a system that's a little bit smaller than that. I mean, El Capitan, the computer, right? And it's about 7,500 square feet, and it can pull about almost 35 megawatts of power. There's about 12,000 nodes. Most of those are compute nodes, right? A little over 11,000 compute nodes. There's a bunch of infrastructure nodes, and then there's these thing called rabbits, which I'll get to in the next slide. And I put a picture here of an El Capitan compute blade. That's the one at the bottom. And so there's 8 blades in a chassis, and the blade is actually 2 nodes. So if you were to kind of just chop that with a cleaver in half, you'd get 2 nodes, one on the left, one on the right. Each node has 4 of these APUs. APUs are, I just forgot what they mean, like accelerated processing unit. It's essentially a hybrid CPU and GPU. And so it's the AMD MI300A series. And so those 4 APUs with memory and such make up a node, and they're pretty dense compute. And we have a bunch of them. All right, so rabbits. What are rabbits? So the basic idea here is we've got a rabbit module that plugs in the rear of a cabinet perpendicular to a chassis of compute nodes. The rabbit consists actually of 2 modules itself. There's a P module, which has actually an AMD Milan processor that's kind of sitting at the top. And that P module runs an OS, runs Kubernetes with management software that controls and allocates the storage in the rabbit module. And then you've got the S module, which is like the 3U chunk below and can hold up to 18 NVMe drives. So this module sticks in the back of this group of compute nodes. So the picture on the left there, you've got, just kind of looks like a standard compute. You've got these chassis of blades and the pretty water cooling hoses. Then you plug in the rabbit module in the back along with the high-speed fabric switches, and you get the picture on the far right there, right? You've got a rabbit module at the tops, which is below that. And then but you've got like a rabbit module for each of these chunks of compute blades. So the way this works is a user in their job script, their little job batch file, they can use a directive to say how much storage and what type of storage they want. And the Rabbit software running will allocate that storage and make it available for the lifetime of a job. This is considered ephemeral storage for the lifetime of a job. And because these plug in directly to a mid-plane in the rack, we essentially have direct copper paths to the storage from the compute nodes. And so there's three ways, I believe, that these compute nodes can access the storage. They can get a local block device, which is formatted as XFS. They can have a remote block device that is available to multiple compute nodes formatted with GFS2, which the GFS handles data consistency, make sure you don't step on yourself across multiple nodes. Or you can do ephemeral Lustre. So you can, these rabbits are connected to the Slingshot network, and so you can have multiple rabbit modules all working together as an ephemeral Lustre file system. So the rabbits are important because we need them to save the main parallel file system, name of Merced, which is coming up. Next slide. So let me give you some numbers. El Capitan is roughly 18 times the compute power of Sierra. El Capitan's parallel Lustre file system is 2.7 times the size of Sierra's file system. Huge disparity. And so how do we not kill the file system? How do we not fill it up, once a week? And so what we really need is for users to do massive data reduction. So we've got these rabbit modules. We need users to do in situ processing, data reduction, data analysis there, and then only send the final product out to the parallel file system. Of course, that's easier said than done. We've learned that a bunch of jobs use their checkpoints for actual analysis too. So that's a problem that we don't quite know how to solve yet. They like to keep all their checkpoints around because they actually use that for data analysis rather than just a never, not just a dumb checkpoint that's never read back. So this is a true big data problem. And we'll find out the answer to that question over the coming years. Will the file system survive? So back to Yosemite. So Merced is the name of the river that runs through the Yosemite Valley. So the systems in this class, in this HPE kind of Cray class of systems, have Yosemite and Sierra Nevada themes. And so Merced is there. It's a big system. It's 42 racks, but it's clearly not big enough. We fear it's not big enough. And so again, that's what we need to figure out. But it's got 50 MBS nodes, 240 OSS nodes. It runs DRAID, ZFS DRAID for the OSTs. I'll get into a little bit more detail that in a couple of slides. And it's connected over Slingshot. One thing different, so this is HPE's E1000 hardware platform, storage platform. Same stuff they put in ClusterStor, except we're actually running TOS on this. TOS is the Trilab operating system. It's essentially a derivative of Red Hat 8 right now. And HPE has been fantastic to work with here. They've been very supportive of us, running our stack and helping every way they can. They've got a lot of great guys, and I just want to say that HPE's been really good to work with on this. Snakes. So I actually kind of like snakes. I know a lot of people don't, but all of the snakes are here because each one of these pictures represents one of our ASP Lustre systems. So what is ASP? ASP, which I've talked about a few times. Sorry if I'm a broken record. But ASP is the adaptable storage platform. It's a kind of a procurement vehicle. It's a 5-year contract. So back in 2020, we put this RFP together, and put it out for bid. It was won by Supermicro. We got in our first systems at the end of 2020, which means we're coming up close to the end, and I hope to get kind of an ASP Next contract out in the next year or so, because I think this has been a success. So what is it? Think of, it's kind of modular storage contract where we essentially have a catalog of different modules and components with static pricing that we can mix and match, put them together to get whatever performance or capacity we need for the solution we want. The idea here is this is not just for Lustre. In fact, we have ASP clusters, of course, that do Lustre. We have a bunch that do HPSS disk cache. There's Globus endpoints. There's Elastic Stack nodes, ones doing plain NFS over ZFS, and probably some other purposes, applications that I'm missing at the moment. It's been well used. We've gotten over 32 storage systems off this contract in the last 5 years, and with a couple, one or two more in the pipeline. And again, it's been a success. And some of the reasons it's been a success, I'll get into now. Typically, I think when in a big data center, you have all these different teams handle different parts of the data center, right, or different applications, right? Maybe this team does NFS filers, or this team does the web stuff, or this team does something else. And what happens is each team kind of optimizes, they find a storage solution that works best for their application, and all of a sudden now you've got all these silos. You've got silos of different storage, but you've also got silos of knowledge inside the data center. And that prevents this sharing of knowledge, and you've got to have a separate inventory for each type of hardware you've got to have, you've got different vendors you're working with for each solution. ASP brings this all together. So now all these different teams, and we have pretty good inter-team and inter-group interaction. A group is actually a formal division of employees at the lab. And we're able to collaborate really well across groups and share knowledge, share experience. We can all commit code, our Ansible code for configuration management. We can all contribute to this, and it's great, for lack of a better word, right? We can share all this. We can share inventory. We have a regular single call with Supermicro, where we can coordinate, any system, in this broad set of systems that needs to be dealt with, and it's really reduced a lot of overhead. It's let us procure things quicker, and we've realized some pretty significant cost savings through it. So, while nothing's ever perfect, there've been bumps here and there. It really has been a win. And so for our commodity Lustre ASP systems, the theme that we went with for those were snakes. And so each of these snakes represents one of the ASP Lustre file systems that we've purchased off the contract. Okay, I'm going a little bit into some technical detail. We're running ZFS 2.2, I think 2.2.7, if I remember correctly. And we used to have everything the same, but with the new kind of E1000 class systems with LCAP and Tuolumne, we've diverged the way we do things a little bit. So I'm going to split these here. But in general, we use NVMe drives for MDTs, and the OSTs are hybrid, a mix of hard drives and NVMe. We use Pacemaker and CoreSync to do the resource management. We tend to do only one single Z pool per OST or per MDT. And then we've really used the Z. The Z is the ZFS event daemon, which kind of comes with ZFS, and it's packed with intelligence, and it does all sorts of cool things for us. So we rely on that heavily. Breaking down the two configs. So there's ASP config. So these are kind of our commodity Lustres. They tend to be mounted, cross-mounted across all the systems on that particular network, widely used. The MDTs there are using two-way mirrors, and that's a kind of a step down from the previous generation. We did three-way mirrors. We weren't completely confident in how reliable the NVMe drives were. They proved to be quite reliable, and so we went from three-way mirrors down to two-way mirrors. And with El Capitan, with Merced, we've actually moved that to RAID Z2, so less parity protection, but we get more capacity out of it. And we figured, given the reliability of the drives, that trade-off was worth it. For the OSTs, we're using D-RAID again. We've been using D-RAID in production since 2020, so we're one of the, we drank our Kool-Aid early on. And on the ASP, we're using a 90 drive JBOD. And so we've got 90 drives in each of these D-RAIDs with 2 logical spares. And each JBOD, so we're probably doing this similar to other people. We have 2 servers and 2 JBODs, and each server can see its peers' resources. It can take over from, those resources if need be for failover. But each JBOD typically has been its own Z pool and its own OST. And it makes for nice management, nice logical separation. But with El Capitan, when we did that, we realized that we could pay a 40% write performance hit by locking a JBOD down to a single Z pool, and we felt 40% was too much to ignore. So we finally gave up and spread a pool across 2 JBODs. And we did this with using 2 D-RAID devices, kind of 2 D-RAID inside of the Z pool. So still 1 Z pool with two D-RAIDs. We found that using 106 drives, because, sorry, these JBODs in the E1000 hardware are 106 drive JBODs. And when we were doing D-RAIDs with 106 drives, we actually got into the case where drives would take so long to rebuild that we would end up having too many drive failures at the same time. And so we split this into 2 53 drive D-RAIDs to give us a little bit less likelihood of having another drive fail while we were rebuilding, and that has worked better so far. I mentioned OSTs are hybrid, so in ASP, we implement the NVMe drives as special devices. So ZFS has this concept of special block devices, and you can configure them in 2 ways. By default, they handle Z pool metadata, or you can configure them to store actual small block, small data, small files and such. And so that's what we're doing on the ASP systems, is we're actually configuring them to store files under 16K. On Merced, we have a lot less NVMe, and so we're just using those drives for Z pool metadata. Moving on to Lustre. So I think I mentioned we've got 9 production file systems right now across multiple networks, across multiple buildings. The ASP systems, kind of we consider our commodity systems. Those are mounted center-wide, center meaning think of a kind of a single network, the same classification of data. So if you go way back in LUG, back in 2018, I gave a presentation on how we unscratched Lustre. We're still that way. So we don't back up Lustre, but it's not scratched. We've told our users, there's a higher class of service. The data will not go away. You don't, it's not your job to migrate it, because the data is just always going to be there in the same path. So users like that, but it created a lot more work for us. So now we have to deal with migrating the data to new hardware when we get it. We've used user quotas to manage capacities, and those have worked quite well. Although we're looking again into project quotas to get take care of some situations that are perhaps a little bit more tricky. And users can go through. There's 3 different tiers of quotas that they can take. Tier 2 is basically free if they ask for it. Tier 3 has a finite time, but they have to be able to justify their allocation too. Okay, one thing that we have that we have that's probably a little bit different from a lot of data centers is fairly complex Lustre routing. So this is a busy diagram, but we essentially have 61 different Lustre networks in Livermore computing by my count. So 8 of those are what we call IB, like SANs. Think of an InfiniBand SAN. The Lustre clusters are attached to those SANs, and the compute nodes can go through gateways to get to that SAN. I'm going to walk through a kind of a sample packet exchange here. You probably cannot see the text very well. Sorry, but I'll try to walk through it. So essentially you have a compute node that sits on Lustre network O2IB10. So this is a private kind of fabric inside of a compute cluster. And then each compute cluster typically has one or more router nodes, Lustre router nodes that sit on that internal compute fabric, as well as on the IB SAN for a particular building. And so this compute node, he wants to talk to a Lustre server that's sitting on the O2IB600 network in a different building. So first, kind of that top yellow box, he looks at his LNet configuration, which we put in etc modprobe.d lnet.conf, and he sees that he's got these, if he wants to get to O2IB600, he needs to go through these router nodes that are on the edge of its cluster. So it goes through those, gets to the next box. Those are the cluster router nodes. For O2IB600, they know they need to go to the building router nodes. So each building has a routing cluster, although we hope that goes away soon. We're playing with direct connecting. So that third box is the building router cluster, and then it routes the packet across TCP0 WAN links to get to the O2IB600, to get to the other building, which is O2IB600, and then from there it goes to the actual Lustre cluster. And you'll see that these later two boxes, well, actually kind of 3 boxes, have a lot more routes defined, and that's because they'll want to know where all the various compute clusters are and how to get to those. Getting short on time, but some challenges. It took us over 2 years to get to Lustre 2.15 from 2.12, not for lack of trying. We ran into numerous Lustre routing issues. On the upper right, you can see 4 bugs that we worked through, and we struggled to find good documentation, but Sergey and I think Amir put up some great documentation finally that we were able to find, and that helped us immensely tuning those. We all of a sudden got got pretty good stability pretty quickly once we got those tunings in. So if you have a big LNet install, I'd advise you to go through that document and make sure you have things tuned correctly. I mentioned migration. When we have new hardware, right, we needed to migrate all the files. So we had written this program script, Lustre fsync, to sync, and we ran into some bugs on some of the later migrations this past year that bit us pretty hard. Things took many more months than expected, and that was due both to bugs and a misconfigured script where we're accidentally doing direct I/O when we didn't, and that would kind of die on some big file transfers. The biggest thing perhaps that got us though was there was a problem. Well, so in the desync program from MPI file utils, it'll go and it'll walk the source, get a list of all the files, and then on the destination, it'll copy all those files. Well, what would happen is, as it would walk the source, it would abort for some reason. Like I think it was due to some network glitch. It would abort, but then return a positive return code. And so the other side of desync thinks that the list of files, which was severely truncated, was the legitimate was the legitimate file list, and it would go through and identify files that now it was supposed to delete because they were no longer on the source. And so it would sync these files, and it would go back and it would delete all these files that it just synced because it thought they no longer existed on the source. So that caused us a lot of consternation. Short story, though, is we still believe in MPI file utils, use version 0.12 and later to escape that bug. Some challenges with LCAP and Merced, really just scalability issues. We ended up changing our pacemaker configuration fundamentally, went from a kind of a centralized pacemaker to now what we call a pairwise, where each pair of nodes is its own pacemaker cluster. Then we've had numerous issues with slingshot stability, and those have mostly calmed down. We still have issues, but we ran into quite a few of those. So time's up, but thank you. I think barely got through, and we can answer some questions.
Do we have any questions for our speaker?
I was curious how you found the pairwise pacemaker configuration to be, and if that solved all the issues you saw with using remote on all the nodes, or if there are still any issues with that architecture.
Good question. I wanted to talk about that more, but ran out of time. So we like the management. We like some things about the centralized pacemaker, but it became clear on Merced it could not scale. It was extremely slow and often wouldn't ever finish. The pairwise is much faster, infinitely more scalable, and I don't think there's another way to go. We do miss the centralized management aspect. Right now, to do any operation, we have to go out to those nodes and run operations rather than just run everything from a single place, the management node. So that's a drawback. I imagine at some time we'll have a script that can kind of do everything from a central location, but for now, we're dealing with it because we have to.
Hey, Cameron, question regarding snapshots, etc. How relevant is that to you? Also, for checkpointing, do you use compression on ZFS? Do you use client-side compression? Do you use LFS mirror extend? Like, for the N+1 checkpoints, are you saving space?
We don't do much of our own checkpointing. That's up to the users generally and user jobs to do checkpoints. If you're talking about snapshots, we'll do snapshots at times before major updates, but otherwise we don't, or if we're debugging stuff, otherwise we don't deal much with snapshots. James, sorry, I'm trying to remember I think there's another question in there I may have missed. Okay, so we use standard ZFS compression. It works pretty well. I think on our ASP systems, we're getting like over 2.2x compression just with standard ZFS compression. So that's working pretty well. We run that on OSTs, not the MBTs.
When you were talking about the rabbits, you mentioned getting users to do analysis and then only copy back to the file system relevant files. How are you handling that? Is that just a user education issue, or are you doing anything specifically?
Yeah, I don't think we have any way to enforce that other than quotas. We have a much, on the closed side of things, we have a much more limited user number of users, and so it's a little bit easier to control. Like we have a good relationship with kind of our power users, but a lot of the users don't care about storage unless it's a problem. And so I don't want to say we need to make it a problem. I mean, it's going to do that on its own, right, with capacity. But we've been trying to reach out and build relationships. Myself and another colleague have been going around to different programs in the lab, among other things, trying to let people know that this is an issue. And I think education is the best way, but I'm sure at some point in the future, hopefully not too near future, we're going to have to do some enforcement one way or another. Maybe limit the tier 3 quotas that we allow.
Do we have any other questions? Let's give a big
Okay,
thank you for our
thanks.
speaker. Thank you very much.